Consider a set of 3 data points. Each data point is depicted by a filled circle and characterized by a numeric feature x and a numeric label y. Machine learning is about finding or learning a map that reads in the feature of a data point and delivers an estimate or prediction for its label. Such a predictor map is referred to as a hypothesis. Here, we depict one such hypothesis by a straight line. Note that while we do not have a data point for every possible value of the feature x, we still can evaluate the hypothesis for any value of x. Machine learning methods rarely use only a single hypothesis. Indeed, learning can only happen if there are several different or alternative hypothesis maps from which one can choose. We refer to the set of hypothesis maps from which a machine learning method chooses or learns as its hypothesis space or model. Here we depict maybe the simplest non-trivial model, which consists of only 2 different hypothesis maps. Probably the most widely used model in machine learning is the linear model. This model consists of all linear maps from the features of a data point to the predicted label. For data points with a single numeric feature x, the linear model can be depicted by all straight lines passing through the origin. Note that each hypothesis of the linear model is uniquely determined by parameters, such as the slope w in this example. The linear model can also be used for data points that have several, say, n numeric features. Here, each hypothesis of the linear model is uniquely determined by n parameters that are used as weights for the features. The value or output of the hypothesis map is the weighted sum of the individual features. Machine learning methods aim at finding or learning useful values for the weights w1 to wn. It can be useful to represent a model using a signal flow chart. The linear model can be represented by a simple chart that consists of a summation unit. The inputs to the summation unit are the weighted features of a data point. The linear model can also be combined with feature transformations to obtain new, larger models. Consider data points characterized by a single numeric feature x. We can then transform this single feature into several new features that indicate if the original feature x falls into a certain value range or interval. The linear model, based on these transformed features, consists of highly nonlinear maps with respect to the original feature x. In particular, each map in the resulting model is piecewise constant relative to the original feature x. Another important machine learning model is based on decision trees. A decision tree is a flowchart representation of a hypothesis map that reads in the feature value x of a data point. In contrast to linear models, decision trees include nonlinear operations, such as testing if a feature value is above or below a certain threshold value. These thresholds are the tunable parameters that are optimized or learned by machine learning methods. An artificial neural network, or ANN for short, is yet another flowchart representation of a hypothesis map. ANNs consist of interconnected basic computational units, which might be referred to as artificial neurons. Each artificial neuron computes a weighted sum of its inputs. This weighted sum is then fed into a nonlinear activation function. Deep learning methods are characterized by using deep ANNs for their model. A deep ANN consists of several layers of artificial neurons, which are mainly connected only between consecutive layers. Like data points, their features and labels, also the model of a machine learning method is a design choice for the machine learning engineer. As for data, also the model design is guided by at least three aspects: statistical properties, the computational complexity, and the trustworthiness of the overall machine learning method. From a statistical perspective, the model underlying a machine learning method should be large enough to contain at least one accurate hypothesis. In particular, if the relation between features and label of a data point is highly nonlinear, then the linear model might be too small. On the other hand, larger models typically require more computational resources. Thus, from a computational perspective, the chosen model must be sufficiently small to fit the computational resources of the machine learning application at hand. To ensure trustworthy machine learning, we must choose a model that consists of smooth hypothesis maps. A smooth hypothesis delivers similar predictions for data points whose features differ only slightly. Another requirement for trustworthy machine learning is its transparency or explainability. Roughly speaking, we prefer models that can be comprehended to some extent by the human user of the machine learning method. One prominent example for an explainable model are decision trees, as they allow to decompose a prediction into a sequence of basic tests that can be grasped easily.